Okay, so today we're going to be doing transformations. We're going to be looking at quadratics, root function, and absolute value as an example. Transformations apply to all though. We're going to be using Desmos graphing calculator. I find this to be a really easy way to understand transformations and really a lot of graphing exercises we're going to do. When you go in here, you can just type out your general function with variables, and if you haven't already clicked, it will ask you if you want to define these variables as a slider. Click that, and now you can dynamically change each variable, and it changes the graph in real time. So if you put the base function you're looking at, and when we're going to do transformations, you can see how it would alter it as compared to the original function. First of all, I want to go over the fact that although transformations do look a little different based on which function you're looking at, there are a great number of consistencies. So let's go from the outside in. A is always going to be on the outside, and it is going to be the vertical stretch or shrink. We can see that in all of them, A on the outside. Then you're going to have your like function operation, I guess I'll call it. The quadratic, you're going to have a squared. Root function is going to be inside square root. Absolute value is going to be absolute value. What's going to be on the inside is going to be k, then in parentheses x minus c. K is the horizontal shrink or stretch. C is going to be the horizontal shift. And then we're going to have add d on the end of all of these. And that is your vertical shift. So with that being said, let's talk about C and D first. These are the easiest. We make minus C so that it operates the way we think it would. We usually associate positive movement on a graph with moving to the right or moving up. So in order for that to happen, C must be negative. So if we want to move to the right 3, make C 3. If we want to move up 2, make D 2. So if we set up our transformations this way, C and D just kind of makes sense. And we can, again, using Desmos, we can watch this in real time as we change these numbers around, which is awesome. And we see that same type of behavior regardless of the type of function we're looking at. So if we looked at this absolute value one, for example, C, negative 2, move to the left 2. D, negative 1, down 1. So C and T, again, pretty intuitive. Let's take a look at A. So A is going to be our vertical stretch or shrink. We say a factor of because this is multiplication. So if we make A 2, for example, for the same horizontal distance moved, we should see the transformation, which is going to be our blue function, go twice as high. So right, a vertical stretch by a factor of 2. So we moved 1, 1 in the original graph. We would expect to move 1 times 2 is 2. Expect to be at negative 1, 2, and we are. And again, we can see that behavior across the board. Vertical stretch by a factor of 2 would mean that we went twice as high for the same horizontal distance. We went 1 in the original, 1 times 2, and we are, in fact, at y equals 2. Good. And, we could go the other way. We could, vertical stretch by a factor of 0.5, or you're shrinking by twice as much. However you want to look at the vertical stretch and shrink when it is phrased that way. But if we made a 0.5, we would expect to go half as far up for the same horizontal distance. And we see that that is true. Onwards to K, which is our horizontal shrink or stretch. We do the opposite here. So a big number is actually going to shrink it. A whole number is going to shrink it. A fraction is going to stretch it. So less than 1, we see that it's getting wider. Greater than 1, it's getting skinnier. So let's make this 2 to be consistent. A horizontal stretch shrink by a factor of 2. We should see that for the same vertical distance traveled, we go half as wide. So let's see if that's true. At 1, 1 in our original graph, so for the same vertical distance, so 1, we would expect to go half as far. Vertical shrink by a factor of 2, horizontal shrink by a factor of 2, and we see that that is so. We went half the horizontal distance. So again, for the same vertical distance, we did a horizontal shrink by a factor of 2, so we went half as far in the x value. And we can see that across the board. We make these k's equal to 2 as well. We should see that they are moved to the left each time by a factor of 2. So horizontal shrink. We see that is so. So if we made k 0.5, then now we have a horizontal stretch by a factor of 2, or a horizontal shrink by 1/2. However you want to look at that. But our expectation for what we would see in the graph is that it would be twice as wide for the same vertical movement, and we see that that is so. Last but not least, we have our reflections. So if we make the function negative, actually let's add a few transformations into there too so we can really differentiate which graph is which. So we're going to reflect this over the x or y axis. Let's see what happens when we make the y negative. We reflect over the x. Now, you're normally not going to see it this way because we're used to isolating y when we think about a function. So we would multiply both sides by -1. Now remember where we were. Negative 2.4, negative 1.3. So we distribute this negative to the other side instead to get y by itself. And we're at the same point. So when we make the function negative, we reflect over the x-axis. Move us back to where we originally were. If we make the x negative, then so we don't need that positive there, we should see it reflect over the y. And in fact we do. So those reflections are the last two pieces of transformations. Remember to include the k, x, and c inside the type of function that you're doing. So this is the absolute value, so the bars are on the outside. This is the root. Again, k, x, and c are all underneath it. Quadratic. Again, k, x, and c all underneath it. So that should do it for transformations.